Okay, yes, today, as Mark said, I'll talk about HYPRE. This is a library of large-scale parallel linear solvers featuring primarily multigrid methods, and I'll tell you more about multigrid in just a minute, but I won't actually tell you lots about it, as was implied by some of the previous speakers. So this is the team currently. We actually have one new postdoc that's not shown here right now. Most of us are part-time, so this team is, the actual team working on HYPRE is smaller than it looks here. There's a website down at the bottom if you're interested in getting more details. And we've been around since probably 98 or so, 1998, and there have been many former members who are on the right here. You have to get used to using the pointer. Okay, so here's an outline of what I'll talk about today. I'll give a little bit of an introduction and motivation about why we're developing multigrid methods in particular, and tell you a little bit about what they are. But the majority of the talk will actually concentrate on these linear system interfaces and how you use HYPRE. This is somewhat of a unique feature with HYPRE, so I'll go into that in a little more detail. And then at the end, I'll say some words about the solvers and preconditioners that are available and some additional information about how to use the package. So first, the motivation. So the reason we care about multigrid is because they are O of n complexity solvers. We sometimes say they're optimal. So if you're solving for n unknowns, they take order n work to do that. And this gives them the potential to scale really well, especially in the weak scaling sense. So if this is a graph that sort of illustrates that. If I'm thinking of growing the problem size together with the number of parallel resources or processors, then I have the potential to have constant time to solution for these larger problems. Whereas with other methods that aren't O of n, you can, even though you're throwing additional resources at the problem, they can still take longer and longer to solve these larger problems. So this is why we care about multigrid. So what is multigrid? Just in one view graph. What I'll do is show you the main components in sort of a cartoon. And here I'm thinking of a two-dimensional Laplacian type problem, which you've probably heard already, and we'll see more of in my talk. So a two-dimensional grid, and this is an iterative method, so you start with an initial guess. And so if you were to plot the difference between that initial guess and the actual solution to the problem, it might look something like this in the top left corner. So the first main ingredient for a multigrid is called a smoother, or it's a relaxation method. And this is something simple like Gauss-Seidel or weighted Jacobi, some very simple method. And after a few iterations of a method like this, what happens in this classical setting is the underlying error is nice and smooth. So I've got to get my mouse back, which means we can approximate that accurately and solve for more efficiently on a coarser grid. So you can see this is a very good representation of that error, even though I've got a quarter of the grid points here. So this is called the coarse grid correction step. We solve for that, and then usually we interpolate back to the fine grid and correct the solution, and that we get very rapid progress towards a solution. But in practice, this coarse grid here, I wish I could make the mouse stay, it can be quite large still. And so what we do in practice is we just reapply this idea. We do additional relaxation, smoothing, coarsen further, et cetera, all the way down to what can just be a single equation, actually, sometimes in the HYPRE library. And then we interpolate all the way back up. And this is called a V-cycle in multigrid terminology because it looks like a big V. So those are the two main components. You have this smoother and then the coarse grid correction, and they complement one another, and you solve the problem really quickly because of that. If you were to count the computational complexity of this, because each of the grid levels gets geometrically smaller and smaller, the overall computation to do one of these cycles is O of n, and it only takes a fixed number of cycles to solve the problem independent of the problem size. So the whole thing is also O of n. Now, this is kind of a geometric picture of what you should think of when you think of multigrid methods. But you can also do this in an algebraic sense, where you're just given a linear system of equations, and you can apply a lot of the same concepts and ideas, but now you only have this linear system. So so you don't have any grids. Instead, you have the graph of a matrix that you can use, and you can coarsen the graph. Then you have to construct coarse grid problems in an algebraic way, et cetera. But you can still make this work, and this is a solver we have in HYPRE that does this, that is probably our big workhorse solver in the library. And to make all this work actually takes quite a bit of research. These multigrid methods apply to smaller classes of problems than like a direct solver would. And so there are lots of different multigrid methods out there, some designed for different classes of problems. And there's also a lot of research to make this thing work well in parallel, both mathematical, math research and computer science research. And here's an example of what you can do after you do a lot of this work to get our algebraic multigrid solver scaling to 1.1 million cores of our IBM BG. And this is a weak scaling plot. The different lines here are just different combinations of MPI task and OpenMP threads. Yeah?
Yeah, I was wondering what application for this is. I mean,
for algebraic multigrid, there are many different applications. This is just a simple, again, just a simple Laplacian problem.
Okay.
Yeah. But it's applied to a lot of different applications. Yeah?
How about the strong scaling?
That's a long, that takes a long answer. Strong scaling is difficult to talk about because there's only so much you can do when you're solving a coupled problem. Strong scaling is always going to roll over, and that rollover point depends a lot on the architecture itself. But then the other thing is that it could be misleading just to look at strong scaling, because what you care about is time to solution, usually. So I can take a really poor, an algorithm that strong scales poorly, like multigrid, and compare it to one that strong scales beautifully, and this can be an order of magnitude faster. So that can be misleading. So it's a hard, you can't really just.
But usually we care more about strong scaling.
You care about time to solution. So if I can solve your problem 10 times faster than another algorithm that strong scales perfectly, you would prefer that. Okay, so now let's talk about how to use HYPRE. So before you get started, there are a few questions you kind of have to ask yourself. There's this linear system interface. We call it conceptual linear system interface that you have to just choose. And I'll talk more about that in a second. Once that decision's made, then you choose a solver or preconditioner you want to use for your application that's suitable. Based on these, you also then need to decide on a matrix, an underlying matrix class that then goes hand in hand with the solver you want to use. Once these decisions are made, then the steps are at the highest level, sort of like this. You may need to build some auxiliary structures. I'll show you how to build grids and stencils in one of the interfaces that those are needed. Then you build the linear system, the matrix, the vector right-hand side. You solve it. Well, you build the solver and preconditioner, solve the system, and then get the information out at the end. So those are the main steps to use the code. So what are these conceptual linear system interfaces that I referred to? This is a little chart that kind of illustrates the idea. If you look along the top, you can think of these icons as representing different sort of applications. So on the right, this is a standard view of a matrix that you would get in linear solver packages. Over here, I've drawn a grid. So you might have a problem that comes from a structured grid with a structured stencil, and it may be more natural then to describe your problem in terms of grids and stencils. So that's more natural. The other thing that can happen if you have this additional information is you might be able to use a solver like this structured semicoarsening multigrid method that takes advantage of the fact that you have structure. And also, you might be able to store it differently and have more efficient computational kernels. So those are a couple of the benefits for having different ways of describing the linear system. But also, you could take this grid stencil interface, and you could still build a general matrix storage class, like compressed sparse row, and then do a general algebraic multigrid method on it as well, without changing hardly any lines of code. So this is the idea that we actually implement in HYPRE. This view graph just goes over the advantages again that I just went over. And in HYPRE, we support currently 4 of these interfaces. The first we call struct. It's for logically rectangular grids, problems that come from logically rectangular grids. Semi-structured, these are problems that are mostly structured, but not entirely. And then another interface called FEI, which was actually developed at Sandia, and we just support this for finite element problems on unstructured grids. And then we also have a classical version of setting up a matrix by rows and columns as you would think of a matrix. So I'm going to spend a fair amount of time actually on the first two because this is what one of the main differences between HYPRE and other packages. Okay, so let's start with struct, which is the structure grid interface. This is appropriate for problems that are on structure grids and have a fixed stencil pattern, also scalar problems on a structure grid. So we have some concepts I want to introduce. We have this concept of a grid, obviously, and we describe it in terms of something called an index space. So for example, this is an I comma j tuple in 2D. And then a box is just a collection of these indexes. So for example, here's a grid down here that consists of two boxes. On the left, the box starts with at -3, 2 and goes to 6, 11. So all of the indexes inside that box are part of the grid. And then here's the second box. And in general, grids are just an arbitrary union of these boxes in parallel. Okay? And in the struct interface, we usually think of the data as being associated with the cell center of these in this picture. Okay? Now, to build the linear system, there are basically 4 objects that need to be built: a grid, a stencil, then the matrix, and then the vector right-hand side. And so I'll go through that for a simple example here, just a Laplacian, 2D Laplacian. And this is the grid I'll choose to use, and I'll use a standard finite volume discretization, so we have a 5-point stencil. And before you describe the problem, it has to be parallelized somehow, distributed. And again, for this example, I'm going to put it on 2 different processors in the way I've depicted here. I want to point out that this is a user decision. You just have to, you can divide the problem up in any way you like. You just have to describe it to HYPRE in that distributed form. And so I'm going to show you the code now that process 0 would use to describe the problem using this interface. Okay? So, and we need to start with the grid. And the way all of these view graphs are going to be is I'll have some code at the bottom. That's the actual code you'd write. And then I'll have sort of a diagram up here that depicts what's going on when you make the calls. So here I want to build this piece of the grid that I showed you before. The first thing you do is call create. You give it the number of dimensions, and it gives you this grid object back. Okay? So that's why I have a grayed out picture up here. The next thing I do is I call this setExtents function, giving a lower and upper corner of a box. So I've done this blue box here on the bottom left. Do it again, and I get the next box here. And then the final thing I do is call a symbol, and I'm done. That's the grid. Process 1 does something similar for its piece of the problem. So the other object we needed to create was this stencil, and I have a 5-point stencil for this problem. So again, I call create, and I give it the size of the stencil. In this case, it's 5, and number of dimensions is 2. And then I make a sequence of calls to this setElement call, which then defines the entries in the stencil. So 0, 0 is the center, -1, 0 is the west coefficient, +1, 0, et cetera, You make this call 5 times, and that's it. Now I've described the shape of the stencil so that now in conjunction with the grid, I understand the non-zero structure of the matrix. A stencil represents a row of the matrix, basically. It's just, now it's sort of described in this more geometric way. Okay, so I've got, after that, then I actually can build the matrix. And this is a 1 view graph sort of example of how that is. If you look at the calls in red, those are the main calls. Again, you call create, you give it the grid and the stencil, you get back a matrix object. You have to call this initialize call, which tells HYPRE you're about to set the coefficients. And then you set the coefficients with set box values calls. And this will do this. I've made 2 calls here, one for the green box on the left, lower left, and the other one on the right. And I've also tried to illustrate that you don't have to set all of the coefficients at once. Here I'm setting just the center and the south coefficient. And in this particular problem, I'm putting a 4 and a -1 in all cases, but this can vary throughout the grid, so it doesn't have to be a constant coefficient problem. I can have different numbers in here. Yeah?
Can you arbitrarily specify a stencil with different, if you want to do some upwinding, for example, can you specify an offset stencil and then specify the weights for the different coefficients of the stencil yourself?
The stencil can be any shape you like. If that's what you're asking. It doesn't have to be symmetric the way I've done it. Okay? So you set the values here, and then you have to do something about boundary conditions usually, and then in the end you assemble the matrix. That's the bottom line. Boundary conditions are done basically through the same set box values call. So here's an example where along this strip, or this little box with this I lower and that I upper, I set the south coefficient to be 0 because that reaches off the grid. So boundary conditions are done something like that. Vectors are similar. I've got a create, an initialize. I set values for the vector for the right-hand side with set box values calls. I don't have stencils to worry about anymore, of course, and then assemble. And that's it. So grid, stencil, a matrix vector, and I have a linear system now that I can then solve. Okay? So one other thing, we do support symmetric storage in this particular interface, and it's very simple to do that. If you have a symmetric problem, you just have to insert this call, set symmetric between the create and the initialize call for the matrix. And then it'll store only half the matrix and take advantage of that. And there's a way to avoid some of the copying, but I'll skip that part. Okay, so on to the next interface, which is a semi-structured grid interface. So again, this is a problem that has a lot of structure in it, but not entirely. Some examples might be this block structured grid here, structured adaptive mesh refinement, which you'll hear more about, or even overset grids, where you have structured grids that overlap arbitrarily. These can all be described through this interface. Another thing that's different between the previous interface and this one is that we can have multiple variables. It's not just scalar values at cell centers. I can have different variables, and they can be located at cell centers, faces, or nodes, and coupled in pretty much arbitrary ways. Of course, the plan is to have as much structure as possible. So if we can use stencils or something like that, we'd like to. Okay, so there's now because this isn't fully structured, we are introducing a new concept here called parts. So we build this out of a bunch of structured parts. And then we have this new object called a graph, which allows us to couple these structured things together in kind of arbitrary ways. And so the graph is built out of either stencils or finite element stiffness matrices. That's the structured component of it. And then you have these other ways of gluing the different structured pieces together. Add entries is an arbitrary way to add coupling between unknowns. And then set neighbor part and set shared part are ways of doing this in a block structured grid setting. And I'll show an example that uses the last two calls next. And I guess I'll have to kind of run through this a little bit. So it's as before. We have the same 4 objects as before, plus this additional graph structure. And let's start with this diffusion problem on this block structured grid on the bottom left. So you see I've got 5 structured components, but they're not glued together in a globally Cartesian way. I've also got 3 variables here, cell-centered and 2 types of face-centered variables, so I have 3 stencils to set up as well. Okay, so in this example, I'm going to define the parts in this way. So 0, 1, 2, 3, 4, and I'm also going to make the decision that each part will be on a single process. But again, this is a user decision. I'm just doing this for the example. Okay, and we'll look at process 3's code. So starting with the grid, again, you call create. You tell it the number of dimensions and the number of parts. Then you actually set the extents for the component of the grid you own. And then you have to tell it the variables that live on the grid. So in this case, I've got cell X face and Y face variable types. And at this point, what I've got is a bunch of structured grids that are completely independent of each other. One way to describe a relationship between them is this set neighbor part call, which, for example, here's the call down here, but what it really does is it describes this blue box in terms of 2 different index spaces, one for part 3 and one for part 2. And it also describes any kind of coordinate transformations that happen in the process. So in part 3, X runs to the right here and Y goes this way, and on part 2, X goes this way and Y goes that way. Did I get that right? Anyway, it's different. So you have a coordinate transformation. And after doing this, then if I put a stencil at this location here, the east coupling will reach out and touch this cell here, and I'll know that it couples to data on part 2. So this allows me to describe the non-zero structure of a more complicated situation. And you do the same thing to couple part 3 and part 4 and call a symbol, and that's the grid. Okay? Just a couple of comments. notice that some of the data actually has different types on different parts. So on part 3, this is an X face, and on part 2, a Y face variable, something like that. That's what the comment down here. This comment actually is pointing out that this is the same variable, even though I've described 2 parts, and originally they're actually 2 different variables. The minute I call this set neighbor part, HYPRE knows that they're actually the same, and then we can make one of them the actual. We can solve for one once and make sure it's the same value. Okay, stencils are similar to before, except that now I've got 3 of them, and each stencil is not only coupled to is also coupled to 3 different variable types. So this Y face stencil couples to Y face variables, X face variables, and cell center variables. Okay, but otherwise it's pretty much the same. Then there's this extra graph thing. Again, you call create, giving it the grid. And then you actually call this set stencil call 3 times, once for each of the stencils, and then assemble, and that's the graph in this example. Okay? To set the values, it's very similar to the struct case. You call this set values or add to values calls, and they're a box version of these as well. Okay? So that's the stencil version of the semi-structured setting. There's also a finite element variant of this. There's some example codes you can look at that illustrate this, and example 14 is going to be in the hands-on as well. It has there are these additional calls. Most of them have the FEM in the name that have to do with finite elements. And I'll kind of run through this quick because it's pretty much the same as the previous setting. I've got this star-shaped grid, so I've got 6 parts in this case. But instead of putting a stencil on this, I'm going to define the coefficients in terms of a 4x4 finite element stiffness matrix that couples these nodal variables on each rectangle together. And then since they're shared, you get an assembly like you would in a finite element setting. Okay, it's similar to before. I've separated into 6 parts, put them each on a processor of their own. Again, the grid is, you create it, you set the extents, and then you have to set the variables again, so it's just a nodal variable in this case. Because I'm doing finite elements now, I set an ordering for the variables in each one of these rectangles, so 0, 1, 2, 3 is what I've chosen to do here. And then to relate the parts together, instead of set neighbor part, I've got this other called set shared part, which is almost exactly the same. But now what this does is say the variables on this left edge, for example, are the same as the variables on the right edge on part 1. And I can make this similar call for the south edge, and then the point in the bottom left is shared with parts 2, 3, and 4. So you have to make those calls as well. And then assemble, and that's the grid. So it's very similar to what I showed before. The graph, again, as before, you call create, and then you just have to make this call that says, I'm doing finite elements, set FEM. You just make that call, assemble, and the graph is done. So the final piece is when you're actually setting the matrix values, you call this add FEM values call instead of set values. And what you do is you pass in values for a stiffness matrix instead. So that's the main difference between this example and the previous one. Okay? And when I showed this diagram in the beginning, I mentioned that you can have a structured grid problem but still build a general matrix object and then do general algebraic multigrid, for example. To do that, between the create and the initialize call for a matrix, for example, you just have to make this call to set object type, which tells it I want a compressed parse matrix built out of this thing. And then at the end, after the assemble, I just get the compressed parse matrix out, and I can use that to call AMG, for example. Okay, so it's just a couple of lines of code that change. All right, so that's pretty much it for those interfaces. We have a number of solvers here in the library. They're on the left here. And in each column here, I have each of the interfaces, the conceptual system interfaces there, and it shows which solvers you can get access to. So the semi-struct gives you access to most of the solvers in the library. Some of them take advantage of structure or semi-structuredness. Some of them are more general algebraic solvers, and then some of them are matrix-free in a sense. They only require an apply of a matrix or matrix vector multiply. Okay, building a solver is very similar to the things I've shown you so far. You create, you set some parameters like a tolerance, or The AMG solver has lots of different parameters that can be set. Call setup, solve, and then you get the values out using the same conceptual interface you did before, and then you destroy the solver. So those are the main steps for all of the solvers in HYPRE. This shows you how to set up a preconditioned, a multigrid preconditioned CG method. I'll skip over that and talk a little bit briefly about the solvers themselves. SMG and PFMG are multigrid methods that take advantage of structure in the problem. So you get access to them through either struct or struct. And they use something called semicoarsening. So in this picture of a structured grid, what would happen is your coarse grids would be chosen. You take every other grid line, for example, to choose your coarse grids. And the difference between the two is the smoother that is used. In SMG, a very strong smoother is used, which makes the method more robust. Applies to a broader class of problems, but it's generally slower and less efficient than this PFMG solver, which uses a simple smoother. Here's the algebraic multigrid method I mentioned. It's called Boomer AMG. You can get access to this through 3 different interfaces. And this is, like I said, really the workhorse in HYPRE. A lot of people use it for lots of different applications. We also have a solver called AMS for Maxwell equations, in particular definite Maxwell's equations of this form, where you have curl plus a positive term here. The negative is an indefinite Maxwell problem, which is much harder than this, and this is hard enough. It actually builds on top of the Boomer AMG solver, so you get all of the scaling benefits that Boomer AMG has in this solver as well. But it applies to all kinds of complicated problems. And ADS is related to it. It's another solver in HYPRE, but it's for grad div problems. We also have a couple of non-multigrid methods in the library. For example, Parasales is a sparse approximate inverse solver. And then Euclid is a parallel incomplete LU factorization method. Okay, so that's most of it about the library. If you want to get the code, this is the link. They also have online users and reference manuals that you can download directly. Building the library is supposed to be very easy, and because it's all in C, it is generally highly portable. You should, in general, have to just type configure followed by make. There's also a CMake option as well, which is better if you're building on Windows boxes and things like that in particular. Configure --help gives you some help information about how to use configure, and here's some options that are most useful, I would say. It's written in C. We do provide a Fortran interface for it, and there's a very close one-to-one relationship between them, so most of the documentation is in C, and you just need to make that translation. And then if you have questions or you have bug reports, or you want to request features or whatever, this is the email address to send it to. If you send me an email, I'll usually forward it to this email as soon as I get the chance, and so it's better just to go directly there. And that's it.